In this video, we'll be discussing how to implement the chi-squared analysis utilizing Excel. Now, there are several ways that you can approach this. We'll approach it in a pretty straightforward way, with the goal being to create the observed and expected matrices and calculate the components that contribute to the chi-squared test statistic based upon those. This method that we're going to discuss today is general enough that you can use it with the goodness of fit test or the test of independence. Recall the only distinction between goodness of fit and test of independence, besides that goodness of fit tends to be a single variable and test of independence tends to be multiple variables, is that in the goodness of fit test, we calculate the expected values based on probabilities listed in the null hypothesis. On the test of independence, we calculate the expected values based on the row and column sums being multiplied together and then divided by the total sum, which incidentally is what is represented in the null hypothesis. That equation is the equation of what should be in the cell if the values were independent. In this video, we'll be discussing specifically how to do the test of independence, though again, the method we'll discuss is broad enough that you can implement it with the goodness of fit test. Note that the calculation of the expected cells is going to be slightly different for the goodness of fit test, as you would be following that different method. But the calculation for the cells in the goodness of fit test is something that is the techniques on how we would do that have been covered in previous videos. All right, so here I'm going to be using the broad spectrum and narrow spectrum antibiotic data set that we used in our lecture slides to give this a shot. Go on and bold my row and column labels, and now I'll just type in the information that I have from my lecture slide onto here. So I just have this on another screen, and I'm just kind of typing it over, 209, 204, and 304, just like that. Now, this is our observed matrix, and I can go on and use this as that. I'll note, though, that when we calculate the expected matrix, we need the marginal values. So recall, we had these values in the margins, and what we can do with this is we can go on and calculate these by using the sum command. Do this for the column values, and hit enter. Do the sum for the second column and hit enter. And this is my bottom margins. And then for the margins on the right, I'll do the sum for the first row and the sum for the second row. And quickly create my marginal values. For my total sum, I can either sum the column values, or I can sum the row values, or I can sum the entire table. Here, I'll just sum the entire table. All three of those should give me the same number, which is 929. Now that I have my marginal values, that is my row sums and my column sums, as well as my grand sum, I can go on and calculate my expected values. Now I'll have the same table setup, MD, DO, BS, and NS. And within each of these, I will quickly going to highlight and bold all of these so I can make sure I'm keeping track of them as my table headers and column and row labels. Here, to calculate the entry in this cell, MDBS, the expected value, I take the column sum for the BS column, the row sum for the MD row, and multiply them together and then divide by the total. So here I'll type equals, grab the column sum, multiply by the row, and divide by the total. And that gives me my expected value. And now just go ahead and do this for each one of these cells. Fantastic. Doing a quick double check with my notes. I see all of this looks on the up and up. That's good. So we didn't break mathematics. We have our expected values here. Again, simply by, for each cell, grabbing the corresponding row total, multiplying by the corresponding column total, and dividing by the table grand total. Now, what I'm going to do is I'm going to calculate the chi-squared contribution. I'll call it the test statistic contribution. And remember what this is for each cell, I do the observed minus expected squared divided by expected for each one of these. So here I'm going to calculate this value for each cell. And recall what we do is we do it for all of them and then we sum them all up. So I'll go on and rewrite my table, BS, broad spectrum, narrow spectrum. Actually, I'll start it a little further over. Broad spectrum, narrow spectrum. There we go. MD, DL, give my tables a little bit of space from one another. And I'll bold these labels. And finally, I'll go on and type in my equation. Equals the, and I'll use parentheses, the observed minus the expected quantity squared divided by the expected. And this is my chi-squared contribution for the first cell, the MD broad spectrum group. From here, I can retype this into each of the cells with the corresponding listings, or I can use the bottom right tool to drag my formula over, and I see that this formula has been updated to represent all of the corresponding cells one to the right of my previous formula. Here I can drag down. We have all the corresponding cells one below the previous formula, and then of course I can drag to the right again to get all the corresponding cells in the one to the right. Nope. If you ever do make a mistake like that, I don't think we've talked about this yet, where I'm clicking and investigating something, what's being discussed, and then I accidentally click on a cell to get out, but now it adds a cell to my calculation. Simply hit the escape key to be able to get out of that very nicely. All right, so now let's go on and calculate our chi-squared value, the degrees of freedom, and the p-value. So we'll have chi-squared. All right, TS for test statistic. We'll have the degrees of freedom. And then we'll have the p-value. Actually, let's go on and let's do the critical value here first. And then we'll do the p-value after that. Perfect. All right, so for the chi-squared test statistic, now that I have all the different contributions, remember the chi-squared test statistic simply sums all of these components together, and that's my chi-squared test statistic. The degrees of freedom is the number of rows minus 1, that's 2 minus 1 or 1, times the number of columns minus 1, 2 minus 1 or 1, so the degrees of freedom in this case is simply going to be 1. To calculate the critical value, I'll use the chi-sq INV, and I'll use the RT version, which returns the right tail probability. This is of less interest other than the fact that I can simply type in the alpha level, and this will give me the correct critical value. In this case, I'll use an alpha of 0.05 and list my degrees of freedom as the degrees of freedom from this cell. I find that my critical value is 3.8415 in this case, and when I compare to the chi-squared, I can see that the chi-squared is greater than the critical value, so I reject the null hypothesis. Recall the null hypothesis is that the degree is independent of whether or not broad spectrum or narrow spectrum antibiotics have been assigned in the most recent case. And in this case, I can reject that. There does seem to, in some way, be a difference. And we can also calculate the p-value. We calculate the p-value by typing the equal sign and then typing chi-squared. And I can see that I have the chi-squared dist. I'm going to use the chi-squared dist RT to calculate the area greater than our test statistic. I give the chi-squared.dist.rt command the test statistic, comma, our degrees of freedom. And again, I'm selecting the cells so that if the cells update, I can update my calculations. One cool part about the way that I've set this up is because all of these cells are calling back ultimately to this original table of 4 values, I can simply change the table of 4 values as my data update, and I can see my new calculations. So here, if I have, let's say, 254 DOs who had narrow spectrum, I can see all of my tables update automatically and find that I have a new p-value. My chi-squared is now less than my critical value, etc., versus 304, which was enough for there to be a statistically significant difference. Now, there is a way to skip these steps and jump straight to a p-value if you have the observed and expected tables. So if you're looking to calculate the p-value by skipping some steps, you can do equals chi-sq, and then use the chi-sq test command. What you'll give it is you'll highlight the observed table values, not the margins, just the original observed data. Then you'll type comma, then type in the expected data values. Again, no margins, just those expected values, and close parentheses. And this will give you the same p-value that we calculated earlier. As you can see, with our alpha level of 0.05, p is less than 0.05, so this test is statistically significant. That is, there is enough evidence to reject the claim that educational background is independent of the use of broad spectrum versus narrow spectrum antibiotics. All right, well, in this video, we've discussed how to implement the chi-squared test of independence. Again, the process is the same for the chi-squared goodness of fit test. The expected value table, instead of doing the row times column divided by grand, you would simply multiply the respective cells by the null hypothesis probability, or using the null hypothesis probability times the grand sum of all of the cells previously, the total sample size, and that gives you your expected values in the goodness of fit test. But here, the last components, all of this other information, this matches exactly with how you would implement the goodness of fit test.